Oh, thank you everyone for your time. Yeah, definitely. I'll present it in English, just because it's a bit too much to present it in Dutch yet. Yeah, so today I wanted to share with you some insights I gained while working on my side projects this year. So this year I wanted to program my site something different than I usually do. So usually I was mostly working on the back end and usually some kind of data intensive applications like statistical workflows, or data warehousing. And this time I wanted to program something really different. So at the beginning of this year, I started with programming a board game. I was digitizing a board game I liked, Planet Steam, but it was still sort of within my comfort zone because it was still a web application in the end, and it was quite reactive, as in not as adjusting to the size of your screen, but as in you send a request and you get a response, then it's being rendered somehow. And the real-time component was, of course, not there because board games, well, the board game is turn-based. So that wasn't. Oh, I forgot to turn my timer. Okay, here we go. Yeah, but my second project, actually, that I'm going to talk about today, was somewhat more interesting and also more challenging. Somewhere at the end of August, I decided to write a real-time game and make it a multiplayer one. But the thing is that I still wanted to do it in a browser. Well, browsers have a lot of nice features that you can just send a link to your proof of concept to friends and get feedback very quickly. You can iterate fast, you can log stuff and have control over it. While with standalone games, well, that's not exactly the case. You have to prepare the blob, send it over, and then, oh, it doesn't work. So I thought it would be a really nice idea to do it in web. And well, that came with a set of its own challenges, and that's basically what this presentation is about, or actually about one narrow topic that pertains to real-time multiplayer games, which is synchronizing the movement. Actually, I had a few other points for this presentation, but in the end I decided to trim down the scope and really focus on just this one, because first of all, I believe this one is actually the most interesting and maybe the most difficult. And also that just makes, I think, for a better presentation. But let's first define exactly what I mean by synchronizing movements for real-time game. So yeah, we're talking about games. So in the end, this is some sort of simulation of the world. And in the world we have a lot of kinematics and physics. And games, are known to exploit the physics. We always have to move, usually shoot someone. So the kinematic component is very, very important. And well, this is a game, and games tend to be competitive. As a multiplayer game, you have to give people equal chances, so that they feel that if they win, then that they got it because they are faster, smarter, better, and not because they had luck. So it's nice to have it sorted out. And how do we sort it out? What kind of challenge is there? So at the heart of it, it still looks like typical boring enterprise application. You have a server, which is a single source of truth, so it's authoritative. All the changes in state come from the server. You don't let clients do crazy stuff for many reasons, but that comes with a lot of consequences. So we already know that people will connect to those to the server from many different machines. Well, many machines, different places, over network equals latency. But we want to sync. So we know that we will not be able to render exactly the same thing. It's just not physically possible. Even if you ignore all the computational cost, network latency, and you just transform it at speed of light, there will be still always some delay. But fortunately, human imperfections, they come for help. And with two nice constants, let's call them. One is 200 milliseconds and the other 50. So the one is human reaction time. Well, reaction time, of course, people differ. There are people like, I don't know, Steve McLaren or Maradona or some other top sporters who actually can react much faster to things they see or hear. But most of us don't. And we make games usually for common denominator or for a couch potato. So if you're within 200 milliseconds for reaction time, that should be reactive enough, especially for slower paced games. And then comes the second one, which is actually much more difficult. this is the 50 milliseconds. Actually, it's even slightly lower than that. That's how fast your eye can perceive a change. And this is actually an interesting topic by itself, but we can assume that if you are well below 50 milliseconds, that means higher than 20 frames per second, let's say 30 frames per second, then most humans will really agree that, okay, I think this is fluid enough. Render in a browser can, and usually if you do rendering properly in a browser, will aim to 60 frames per second, but for many applications it would be an overkill. Okay, so knowing those constraints, and knowing that we have multiple clients, we also know that we have to send some kind of order. That I want to move, and I cannot say move to position 1240. I want to ask nicely the server, regardless of where I am, you know my position, I want to move forward. And after the server actually propagates this change, it's being displayed, let's say in rough terms. So that means that quite a lot of stuff needs to be done on the server. And when you look at those numbers that I showed previously, so 50 milliseconds and 200 milliseconds, well, those constraints kind of build up. And whatever type of logic you add to the movements, that actually adds up to what you have to calculate within the tick rate. So whenever I have, so basically the more clients I have, basically all those operations will increase in cost with numbers of players. And even worse, some of those computers are actually quite heavy, like collision detection. And even broadcasting the change itself can be actually quite cumbersome, depending on how much events you have to do. So a lot of optimization you have to go in there. So that sounds actually quite daunting, that you need to process a lot of stuff that grows really fast with numbers of players. And yeah, and you have to do it within those confines and then render it. But hey, in the end of 90s, there were games like that, standalone ones. Well, that's actually not from the 90s, it's already Counterstrike source. But already in the end of the 90s, you could play those games with up to 16 players. And yeah, I mean, it was good enough. Of course, latencies were pretty high, around 200 milliseconds, but you could play, you could shoot somebody. There were even tournaments. And it kept growing and improving. Yeah, actually, this picture specifically, it shows already an interesting concept, and it relates to the latency. So this phantom behind, that shows difference between position as it's supposed to be and the position that's actually being rendered. And this is because what you get on the client is, of course, delayed. But I will come back to this trick and why do you actually display not something that you get immediately, but something more in the past in a few slides. But yeah, okay, so we know that this is what we are used to since the end of the 90s. But this is more likely what we're going to find in the web. This is Agar.io, one of the most successful games now on the web. I mean, of course, measure successful, but the real-time games, multiplayer games. And actually it's built over WebSockets. Yeah, and those sort of games tend to have very symbolic graphics, and they use WebSockets overwhelmingly. There isn't really that much more choice as far as I could find. There are some new upcoming libraries and other interesting approaches like WebRTC. Actually, I'll come back to it at the end. But overall, this is what you get. This is what you had in the end of the 90s with super high tick rates and graphics, flying gore, all the stuff. This is what you have in 2017. Yeah, so what is the reason for it? I mean, I understand that the browsers, they used to have a lot of issues, JavaScript and stuff, and Canvas isn't really, is quite young. But is this really caused by Canvas, JavaScript, and browsers wars? No, not quite. So yeah, this is basically, I was hoping for some player called UDP to come with a, I don't know if you're acquainted with how Agar.io works, but that you basically go this blob, you name it. I named my own TCP IP, and then if you meet a smaller blob, you eat it, and if you find a bigger blob, then well, no luck, you are being eaten. I was hoping for a player called UDP to eat me, because all those people who implement those nice standalone games back in the 90s, and still implement them till today, they use UDP, which is another protocol built on top of internet protocol for sending packets over the net. And yeah, on the browsers you cannot use UDP, which is simply said just faster. It doesn't really give you that much less latency. You still have to deal with actual delay. That's impossible to overcome completely, but just the rate at which you can send it and also overhead of keeping connection goes away. Because guess what? In UDP you just don't have a connection. Just send a packet and it's fine. And yeah, and TCP is much more, let's say, corporate. It's more about confirmations, assurances, order. This is what's actually nice for many web applications, where you want to know that if you open a connection and you send 2 messages, you would like to be sure that they arrive at in the same order, and that they actually will arrive. And you would think, okay, but don't I need this sort of assurances in a game as well? Is it actually good? Maybe TCP just solves a lot of issues for us, and you would need to implement some kind of reliability on top of UDP. Sure, you actually do need to have a lot of reliability in UDP, but not that much for games, because there comes a really interesting paradox. So while TCP really makes sure that you get the packet that's being resent if it's not, and yeah, you get the response when it actually was delivered. Yeah, this increases latency so much that in case of games in which each packet actually has limited shelf life, and they're like, yeah, it's all could recur, but I don't no longer care. So, simply spoken, UDP is good enough in reliability with some additional tweaks and cheats you have to implement on the client side, and all the overhead from TCP is completely not suitable for real-time games. Yeah, so this is a pretty grim way to start a presentation about making real-time games in the browser. Yeah, this is what we'll have to live with, and especially look at the numbers at the bottom. Typical tournament server for Counterstrike source operates at 128 ticks per second. That means that update to the state happens 128 times. If you divide 1 second per 128, that's slightly lower than 8 milliseconds. So yeah, let's come back a bit to this table. Yeah, of course those time complexity estimations are mostly for unoptimized versions, but still, you have to calculate all of this stuff and send it, and all of that has to keep pace with 8 milliseconds. That's pretty tough. Yeah, but guys in the 90s could do it, then apparently it's possible. Anyway, on the WebSockets, because of the connection overhead, and yeah, because it's TCP, you are not likely to get 128. And actually, in a few moments, we will try. Yeah, how would we go about implementing that anyway? Let's say we want to think, okay, I understand there are all sorts of trade-offs, and web isn't exactly a platform for real-time games, but I'll try anyway. And not knowing that much about how games are really made, I thought, okay, so let's start with some naive implementation. I'll just have this server, and first I was prototyping it. I wrote it in Python with Tornado, but later on I switched to Golang just because. Oh well, also actually I had good reasons for it, but I'll come back to it later. Yeah, and I thought, okay, let's make a proof of concept, just a small demo. I will open the browser, immediately get a connection, and get the position from a server, and then every next client who comes in will also get the position. Every time I make a move with Wsad, a command will be sent to a server, resolved by a server, and then immediately all the positions will be updated for all the active clients. Yeah, I mean, that sounds kind of straightforward, right? I mean, that sounds like common sense. I send an order, a command. There's command pattern over web service. It's actually a nice thing, by the way. I also want to talk about it, but I think that the time will not allow. And yeah, then you just send updates. What's the big deal? And you can actually have a look how the naive implementation works if you go to move-sync-demo.geku.com. I'll just restart the service. I have, so you move with WSAD. And actually, you say, yeah, I mean, it kind of works, right? I mean, you see people moving around, and there's quite a lot of us. I mean, of course, it's extremely simple, and there aren't any obstacles. And yeah, so basically, you have multiple browsers over a network, and you get position synced. And then you see, I have a small assistant to help me with my presentation. Is the guy who's very frantically circling around. And this is the bot. Say hi to bot. And this bot really shows it really nicely that what really happens here is really a kind of like a lockstep update, just like. So that's the frame rate simply is too low. And why is that? Yeah, I mean, you simply your tick rate is a frame rate in this naive implementation. And yeah, so this is not exactly sufficient. So let's say, okay, so my tick rate is a frame rate, it's fine. Let's just try to increase the tick rate. So I'll just go and kill the server. So apologies for your loss of connection.
Oh, my state.
All right, and where is that? And now I'll just increase the update rate. Let's say 20 milliseconds. And let's say I'll add some bots, and I'll turn the collisions on.
No!
No.
All right, and I'll refresh.
Refresh.
I need. Netwerk is over plus.
I'll stop refreshing.
Why doesn't it respond? Ah, of course, I forgot the address parameter. Yeah, now it should be fine.
Wee! Yay! Oh, that's
so
fast.
fast.
Way fast.
Yeah.
Ja, wie ben ik?
So,
Ah,
so yeah, so basically, did I solve the problem? Yeah, I mean, now I have a wicked fast update rate. Yeah, everything looks to be smooth and even faster. And of course, I can also change the actual speed itself just basing parameter. But yeah, that's fine. Should be fine, no?
I'm not sure if collisions work though.
No, I turned off collisions.
Oh.
Now actually, so let's add. Okay, I'm very happy and content with my game, and I'll add collisions. And let's say I'll have more players, more bots, business is growing strong. And bam! What's going on?
Wie ben ik?
Does it even load?
Ow.
Does that even load? Yeah, it actually loads. Yeah, so basically you would think, yeah, why bother with all those optimization and stuff? You can just increase the time rate. Yeah, but
Terminal going insane, man.
yeah, there's some stuff that shouldn't be there.
Yeah, that's probably the bottleneck at the most.
Yeah, probably the biggest bottleneck is the one log print statement that is not supposed to be there. All right, so I should basically close my laptop and go on and say, okay, now I'm a game developer. But yeah, let's come back to the presentation. There are some issues here that cannot really be solved with just increasing the rate, and the rate itself is sort of lame because. Like you remember, every time I want to add something to my logic, let's say I want to add triggers. Let's say there's a scripted event, and if I walk into a given area, so it'll be a collision detection event, and it will trigger some action. Basically, I keep adding logic to this already very dense loop that happens every tick rate. And yeah, but I still have to maintain insanely high tick rate just to have high frame rate. That's really lame. And on top of that, there are some more issues caused by it that will be not solved just by increasing the tick rate. Okay, so basically the solution would be just to decouple the tick rate from the frame rate. So a better implementation would be, all right, so yeah, we have plenty of people who have developed for the web, and probably you've heard about optimistic resolution. Basically, the problem that we have now here is that I get some updates, and I know that action taken by the player is almost certainly going to be resolved successfully. In those cases, I'm optimistic, and I say, yeah, I'll be fine. And I just pretend that it actually already happened. So let's say I say, move forward. And I don't wait for the server to actually send me the next position, because I know my speed, and I know direction I moved in, and I also know all the directions that other players or other moving objects have taken. So I can just extrapolate that for a given period. Of course, if you extrapolate for too long and have, let's say, update period of half a second, then people will start walking into the walls, and then you will end up having to implement collision detection. But it's not entirely necessary. You just extrapolate for some time and then wait for the next update to come. And will that actually solve the problem? Actually, the term that I used here is not correct, because in fact, what we do is that at the time that update arrives, I immediately render. There's one problem here. So if you walk, let's say, on a straight line, if I try to show that, okay, maybe I'll decrease the tick rate a bit to make it practical now. All right. So not only is it about the slow, the movement is not slow, but it's also inconsistent. So if you look closely, or if you play long enough, or if you're immersed, especially if you have actually some kind of surrounding, if you have other obstacles and background, then you see that it moves in this kind of movement. And this is basically caused by network jitter. Yeah, so not only do we have to deal with delay and connection overhead, but we also have to deal with the fact that the latency itself is just not consistent. At a certain time, it will be actually faster to deliver your update, and sometimes will be lower. So you have to account for the variation in the latency itself as well. And then we arrive basically at the algorithm that guys behind Counterstrike source used over the UDP. And actually, you can also use that over WebSocket just with slightly different parameters. So basically, the solution here is still very similar to our better one, that we still rely on kind of optimistic resolutions, but instead of extrapolating into the future, we actually do a slightly different trick. We accept all the messages, put them in a queue, and then we pretend there's actually around 200 milliseconds back in time. And each message itself is actually timestamped by the server time, not the client time. That's actually very important. Otherwise, you have the bias of the jitter again. So I get those messages and I don't immediately render them. That comes from interesting, one of those biases that we humans have. Humans don't really care about seeing exact thing at the exact time. It's actually pretty fine to delay within the past. Even in Counterstrike, where it's really important that you see the exact picture of the guy you're going to shoot, they actually do that. And they actually use parameter, I think between 150 milliseconds of delay. So I guess in our Agar.io style game, you can allow that as well. But what do you do then? Okay, now we delayed that, but how does it solve jitter? So I have in my queue 3 positions. And I know that the latest one might have come on the right time, but there's around 30–40% chance that it's either slightly too early or too late. So I know that this variation of the last message actually causes the jitter. So I can actually skip this latest message and operate only on the one just before, and then n-1 than this one. Or if I have just very ample tick rate, I can operate on more messages, but still within a range that does not include the latest one. It's very important. So let's see how that works in practice. So I'll have to kill the process. Sorry.
Oh, ik heb het wat. Ik zag er allemaal speed up, dat is mooi.
Whoa, someone's coming real fast.
Right, and now welcome to the world of smoothness, where even my bot assistant can just frolic around with a perfectly smooth motion. Yeah, I guess it's of course still not perfect. There are a lot of small optimizations you can add. This is just a technical demo. Essentially what you see now is the implementation of what guys behind the source engine published in a, let's call it semi-detailed white paper over how the system works for Counterstrike. It was very helpful in implementing that. So I was happy that worked out. Also, we can have a look at the code itself. It's in my GitHub account, my difficult name and difficult surname / realtime move sync. And it's like a pretty self-contained repository where you can play around with this simple proof of concept, modify it slightly. My intention with this small side project is to make it into sort of a mini tutorial and just keep it as a repository, clean this up a bit, so that other people or me in the future can start a project for multiplayer game in the web easier. Because there still isn't really that much material on the net that you can really use compared to what you have with standalone games. There's basically nothing. And what I used on my journey to learning game programming. One book that was really instrumental in that is Game Programming Patterns. It's absolutely amazing. Actually, it's even good just for your general programming knowledge because it covers a lot of patterns that are not really that terribly used outside of game programming, but can sometimes be applied. One pattern that I like the most and that I used in some of my side projects, especially the board game one, was the command pattern. But it won't be time to cover this one. There are plenty of other nice ones, especially about optimization, like creating object pools, or about, say, how can you apply more common traditional programming patterns in game environment. Really good stuff. Second position is, of course, the article published by Counterstrike guys. That's the first link. Actually, I will share that. They describe in some detail exactly just what I told you. Of course, they worked over UDP, so the tick rate is higher, and the buffer size is different. But and of course, they have to account also for unreliability. We have to work with a shorter buffer, but on the top side, we don't have to implement additional control checks, so that's pretty good. And there's also another one, that's the MDN Game Center. So HTML5 canvas is actually pretty, in my opinion, pretty mature, and you can do a lot of cool stuff with it. And there's a lot of nice article there how you can write games that just run smoothly, and how you can use WebSockets for games and maintain connection correctly. Really nice some sorts of information. Well, thank you for listening. Yeah, I encourage you to visit my GitHub page and maybe check out the project, maybe contribute, and then we can maybe make it into a nice tutorial and use it in some other side projects in the future. Thank you. Are there any questions?
Are you gonna make a finished game?
Finished game. So finishing things. So my goal with that is for now to make a tutorial, to make kind of like a solid base for myself and for others to make this sort of games. And making games will be something that will come after that. Because let's say when I was making the board game, it was relatively easy because I still could use most of my skills just for normal web development. It wasn't really that much different. But in this case, I actually had to learn a lot. And I realized that the code I ended up with writing just for so the end game I wanted to make was full of proof of concepts and trials. So I decided to scrap that and just make this simple repo, which is just focused on the technicalities. And once I have this sorted out, I can proceed with making something creative.
Cool. And also, have you looked at Gaffer Games, the website?
What games?
It's a blog by Glenn Fiedler, which I have looked at in the past for things like this. He has many interesting tutorials and blogs, and explains
cool.
a lot about this.
No, I haven't. Actually, I would love to read that.
Gaffer Games. I will send it to you.
Great, thanks.
I noticed a bit of input lag on the demo that's running now.
Yeah.
Is that because there's still something to implement, like something to
So
remedy?
there are actually two things that are happening there. One part of the delay you're experiencing between the time you press a button and you see a reaction, small part of it, is intended. So that's the the constant that we use, that we travel back in time. But there is a chance that it actually will be higher because there's also latency that we try to estimate. Every update comes with a timestamp from the server, and as soon as it comes, the first one, the registration one, we estimate the latency. And this latency estimate is used to subtract it from the delay, so that the delay is not longer than necessary. Unfortunately, the mechanism that I implemented here is a bit lame, because I estimate the latency only during registration. So when you open your browser, it estimates just once. But of course, the latency, this is it's also subject, of course, to jitter. So there's a chance that your estimate for latency was not correct. So what would be good to implement in this repository as well would be progressive updating of latency. So let's say every 60 or 20 updates to add to a list of latency measurements the difference between the client registered timestamp and server registered timestamp, and take, let's say, a median value out of it. Then you will be less likely to experience a bigger delay than is necessary.
And what about optimistic rendering of the player input, as in just show the player where the client thinks the player is, and and not where the client thinks the server thinks the player is?
Right, that's a good one. That's also something that should be implemented in this repository, because when you combine the optimistic resolution with interpolation, then you can really have a much bigger buffer. That's just a better way to do it. Yeah,
The problem there is that you'll have to create all the logic on both the server and the client side, right? Because then they both need to know how to render the physics, for example, or you have to do it on both. Yeah,
so I promised to come back to this picture, and it's actually quite some interesting articles on the net on how Counterstrike does that, because they have advanced significantly over the years. Okay, how many of you actually played Counterstrike? And did you play the first Counterstrike, the one based on Half-Life?
Nope, that I won.
Great, so you remember how you had to shoot a little bit in front of people just to hit them, especially if you had crazy latency. Yeah, when I was playing back from Eastern Europe because I crappy latency. So this was the first thing I learned about Counter-Strike, that you don't shoot at the head, you shoot in front of the head. And that nowadays has been greatly improved. And actually older players who come back, they can be actually quite confused because they shoot in front and they actually shoot in front and that doesn't hit. This is because of that. It's sort of like a situation when you are at the crossroads with many people trying to pass and there are no lights, and everyone assumes that the other one will let you go, and then everyone ends up crashing. And it's also a fight between people who try to predict what happens next, and if both server and the client do that, then of course you will not get the correct position. But nowadays in Counter-Strike you can just shoot right at the guy because they estimate latency and subtract it from the displayed state. If you shot at given place, then it kind of travels, the bullet travels a bit in time back to actually resolve that. Yeah. Any more questions?
Back in time to resolve.
Yeah, sorry, I'll be more precise. Okay, so I shoot you at the time 10, but this is the position that was given to me with some latency. So you issued the command at time 5. I see it at time 10. It is somewhat unfair if I resolve it at this time, because I will not be able to see what happens in the meantime. So they were allowed to travel as if you
shot at 5 seconds.
Yeah.
5 ticks further earlier.
Yeah, and this is unnoticeable for a player, that it actually kind of rolled back 50 milliseconds of his life, and then, oh, actually you didn't move there, actually you died. That's fine with humans, because we are very imperfect. Okay.
Literally my only takeaway here. Yeah. Humans are very imperfect.
But that's good because of websockets. Right, any more questions?
Do you need to worry about Nagle's algorithm?
Sorry, again?
Nagle's algorithm? Or Nagel? I don't know how to pronounce it.
Nagels, I don't know that.
That is buffering input messages. So the thing with Nagle's algorithm always comes up when you have these real-time things.
Yeah.
So if you have, wait, let me see if I get it correct.
What Nagle does is you first open a connection to the server over TCP, and then you're sending messages to the server. But Nagle is buffering if you're having lots of small messages into a buffer, and then emits them to the server, so you're getting delays.
That's actually the opposite of what you'd want with games,
Exactly.
right?
Yeah, exactly. You don't want to do this, so you want to disable Nagle for most of the
Nagle
things.
is client side, right?
But I've never heard of it, how to do that in JavaScript actually, so I'm not sure if it's possible.
Yeah, I guess that's something I have to research. Maybe add to the repo. It's a good one, thanks. Yeah, actually, of course, with buffering is also one bummer when it comes to JavaScript. So let's say if you have a client written in C++ or anything else in JavaScript or interpreted language, and you keep a buffer, and you want to do operation in JavaScript is L shift, then this L shift is, the complexity increases with the size. And let's say in C++, Rust, Golang, you actually can at a constant time scrap first element. So in my code, if you look closely, on each queue for each position, I maintain a queue of position, let's say time series. And every time one point is added, and I check if other points are outdated. And if they are, I scrap them, and it's used by L shift. Yeah, so for the sizes of the queues that we maintain, because our buffer isn't really that generous, it's maximum of 5 elements, it's not that big. But if the buffer were to be bigger with higher tick rates, then the overhead would just become bigger and bigger. All right, if there are no further questions, then yeah, I encourage you to check out my code and play with it and maybe contribute. That would be great.
Cool.
Thank you for listening.